put that on stage. And we're going live. Sebastian, can you hear me okay? Let me know in the chat. This is wonderful. I don't know. We'll see. There's like a 5 to 10 second delay. And then he's got a response. If he can hear me, he might not even be able to hear me.
There's no viewers.
Oh, he left. So sad. Okay, that's fine. Let's just play cozy jazz. I need to make sure the volume works. Volume's up. Yep. All right, there's volume. I think we got sound. And a really bad lag. Wow, the internet's struggling today. All right, I think we're good. Okay. Turn that off. All right, let's get started. All right, so I left off. I went all the way up until I covered all the SAT math stuff. So all that's left is what we've done in the second quarter. It used to be Chapter 6. I just rebranded it as Unit 1. So this is going to be the factoring and solving that we did within the first unit. So a lot of polynomials, a lot of factoring. Oftentimes the directions are going to be very direct as to what to do. So pay attention to that. That can be very helpful. So we want to start by factoring out the greatest common factor and simplify the factors if possible. So checking to see, can we factor any more, or can we simplify after we factor out the GCF? So we're looking for the greatest factor that can divide into all the terms that are given. So we start looking at the numerical factors. 4 and 20 can be both divided by 4. And when we look at our variables, we want to take the smallest exponent. Since 1 is the smallest, our GCF is 4x. So both of these terms will be divided by 4x in order to factor it out, leaving me with x squared plus 5. There's no additional factoring that can happen there, and we did indeed get the greatest common factor. So that is our complete factorization. Looking numerically, we've got 28 and 20, and our greatest common factor is going to be, looks like 4 again. So GCF of 4. And then among our variables, for x, the smallest exponent is 4, and for y, the smallest exponent is 3. So x to the 4th, y to the 3rd. So all of these terms divided by 4, x to the 4th, y to the 3rd, and so on, giving us our greatest common factor. On the outside, 28 divided by 4 gives me 7, x to the 5th, y to the 5th, minus 20 divided by 4 is 5. The x will cancel out, leaving us with just y to the 3rd, and then plus 7. X to the 3rd, and the y's will cancel out, leaving us with just that. And there is our GCF. Here we have a binomial greatest common factor. We have 2 terms, both of which have 2 factors. One of those factors just happens to be 2 minus m. I can get that to erase like I wanted to. No? Okay, that's fine. Let's just be like that. There we go. So 2 minus m is going to be our greatest common factor. So we divide both of these by the binomial 2 minus m. So that will come out. We're going to keep it in parentheses. When that cancels, we're just left with the terms t plus s, again in parentheses. Moving into factor by grouping, this is always done when we have 4 terms. And so we're going to split the polynomial in half, and we're going to factor a GCF out of the first 2 terms, in this case 5x, leaving us with 2x minus 3. And on the right side, when we factor out the GCF of -6, that leaves us with 2x minus 3. Again, our goal here is to make these binomials the same so that we can then factor out that common binomial of 2x minus 3. Don't know why I wrote an x there. Ignore that. And when that gets eliminated and factored out, we're just left with the binomial of 5x minus 6. Again, 4 terms, factor by grouping. Our GCF here is 4x squared, leaving us with 3x squared plus 2. Since our goal is to get 3x squared plus 2, we just need to consider what it is we can factor out. If I factor out a -5, then I'm left with the 3x squared plus 2. So we have that common factor of 3x squared plus 2, and then 4x squared minus 5 is what we're left with after that is eliminated. Trinomials, these are our bread and butter. A lot of these show up in a lot of places. We've done a lot of the factoring earlier in the SAT, so then we're just kind of solidifying this a little bit further. Again, we're looking for the product of C, which in this case is -12, and 2 numbers that add to give us the value of B, which in this case is 1. If we consider all of our factor pairs and their combinations, plus and minus on everything, we want to try to find 2 numbers that'll match up and give us the result of -1. That's going to be a combination of 3 and 4. Since I want my sum to be negative, that means that I have to have a +3 and a -4. Now, we can do factor by grouping, but because our leading coefficient is 1, we have a shortcut in which we can just use those 2 factors as the constants in the binomial factor pair. It's always a good idea. You can double check your calculations, make sure that your factors actually give you the result that you want. A really quick check is doing just the first and the last multiplication. A lot of times that'll kind of give you the idea of what you're looking for. I know when I multiply the first 2 terms, I get my x squared back. If I multiply the last 2 terms, I get my -12. And if I add these together, I get -1. So that's a quick mental check you can do to make sure your trinomial is factored out correctly. Here we do have a leading coefficient, but we also have a greatest common factor of 2. So we'll start by factoring that out, leaving us with x squared minus 6x plus 8. Then we can proceed with our product and sum. So our C value is 8 and our sum is -6. Again, considering all of our factor pairs for 8, I've got 1 and 8 and I've got 2 and 4. The only way to get a 6 is with 2 and 4. In order for our product to be positive but our sum to be negative, both of those numbers need to be negative. So -2 and a -4. They will multiply to 8 and add to -6. Our leading coefficient is 1 now, so we can apply our shortcut, x minus 2 and x minus 4. And then don't forget to bring down that greatest common factor. So our complete factorization is 2, x minus 2, and x minus 4. Looking here, we're going to check to see if we have a greatest common factor. I have a sinking suspicion. I'm looking at 27 and 90, and I see, okay, I've got 9 and 3 as options. So I'm just going to check to see if 117 is divisible by 9 to start. It is. So our greatest common factor is going to be 9. 27 divided by 9 is 3. X squared minus 117 divided by 9 is 13. X, and then 90 divided by 9 is 10. Okay. So we factor out to GCF. There's no other greatest common factor because 3 and 13 are prime. So I have a leading coefficient that's not 1, which means for my product, I have to multiply A times C together. So we want the product of A times C, which in this case is negative 30. And I want a sum of negative 13. The two numbers that will achieve that goal for us are going to be a negative 15 and a positive 2. Negative 15 and positive 2 will add to 13, and we'll still multiply to negative 30. Now, we can't apply our shortcut because we have the leading coefficient, so we're going to need to split the negative 13x into those two numbers. So we're going to take the negative 15 and write negative 15x. We'll take the positive 2 and write plus 2x. And then we'll just write the A term and the C term out in the front and the back respectively. So we've taken our trinomial and split it into 4 terms so that we can apply factor by grouping. So I'm not going to keep writing the GCF till the end. We're just going to make a note that, hey, we need to bring that down. So the GCF for the first 2 terms is 3x, leaving us with x minus 5. And again, we need to be left with x minus 5 on the right. Factoring out a positive 2 achieves that. So we have the matching x minus 5, and we're left with 3x plus 2. And then again, we just want to remember to bring down our greatest common factor. We have a GCF for 18 and 15. That's going to be the number 3. And because we have a leading coefficient that's negative, it'll be a lot easier just to factor out a negative 3 to simplify the factoring. So we're going to be left with a positive 6x squared, a positive 5x, and a negative 6 for our C term. Then we can look at our product and sum pair. We want a product of A times C, which is negative 36, and a sum of 5, 9 and 4. If I have a positive 9 and a negative 4, that'll add to 5 and multiply to negative 36. So we have 6x squared plus 9x minus 4x minus 6. So we, again, split that 5x term into those two. Factor by grouping. 3x leaves me with 2x plus 3. And I want to be left with 2x plus 3 over here. In order to do that, we need to take out a negative 2. So we have 2x plus 3 and a 3x minus 2. And don't forget our GCF of negative 3. Just be very, very careful when you do factor out that negative GCF. Again, your signs will switch. So just be very diligent about tracking your positive and negatives as you work through those. How are we feeling so far? Killing it. All right, so we've got 49, 112, and 64. There's no GCF here, and a lot of students are tempted to just go ahead and start to multiply, but you notice you're going to get a really, really big number, and that's really obnoxious. If there's no GCF and you find your product of A times C, chances are you have a special factoring. So take a look at the structure and pay attention what's special about these numbers. 49 is a perfect square. It's 7 squared. 64 is also a perfect square. It is 8 squared. And so if we, what we might have here is a perfect square trinomial. Perfect square trinomial, which results when our first and last term are perfect squares. If I multiply 7 times 8 together, I get 56. And then when I double it, then I get 112, which is my middle term. This verifies that, yes, we do indeed have a perfect square trinomial. So factoring it is actually really quick. We take the square root of the first term. We take the square root of the last term. We take whatever sign comes first, put it in a binomial squared, and we're all done. So big hint when you try to do A times C and there's no GCF and it's a really, really big number, you probably have a special case factor.
Sorry, what was it? 7m? Oh, just minus
7m minus 8 squared. Mm-hmm. So we're not given much direction here about factoring, so we want to make sure we're paying really close attention to the structure and formatting. Whenever we have a binomial and there's no greatest common factor, then the only thing we can do to factor is one of the special cases, either the difference of squares. Oh, there we go. The difference of squares. So x squared minus y squared. The difference of cubes, x cubed minus y cubed, or the sum of cubes, x cubed plus y cubed. And again, x and y can just represent any expression that has been squared or any expression that has been cubed. It doesn't have to be those variables specifically. So we want to, again, analyze that structure and pay attention and make sure that we have that structure there, and then we can factor it using the formula. So I have y squared, which is y being squared, and I have 4, which is 2 being squared. So I have that difference of squares. The difference of squares. And our difference of squares always factors to be 2 binomials where I have the root of both of those expressions, one with a plus and one with a minus. So the square root of y squared is just y. And the square root of 4 is 2, one with a plus and one with a minus. We've got a binomial, but don't forget, we can check for GCF. Might be tempted to think it's a difference of cubes because our first expression is cubed, but our second expression is not cubed. So we factor out the a first, and then we are left with 64a squared minus 25, which again leaves us with a greatest common factor, or a difference of squares. And so we will have 2 binomials. The square root of the first term is 8a, and the last term is 5, one with a plus, one with a minus. All right, let's keep chugging along. No GCF here, but we do see that we have some cubed terms, and it is subtraction. So we have a difference of cubes. The difference of cubes will always factor to be a binomial and a trinomial. The binomial will just be the root of whatever those terms are. And then from there, we're going to build the trinomial based off the values we have inside the binomial. So we'll square the first term, we'll multiply the 2 terms, and we'll square the last term. The signs are going to follow a pattern, same with the sum of cubes, where we're going to match the first sign with our original polynomial. We will switch the second sign and then always add on the third. So it's going to be a match, a switch, and a plus. And the same thing goes for the sum of cubes. If I have a cubed plus b cubed, all the terms are going to be the same, a and b. And then we're going to square. I forgot to write the square. I said it, I just didn't write it. We're going to square the first one, multiply the 2, square the last one, and then we're going to have a match, a switch, and a plus every time. So we're going to look and see the cube of my first term, or the cube root, is going to be 4a. The cube root of my second term is 5b. Now that I have that, and I need the minus sign. Now I don't need to look at this anymore. My trinomial is going to be my first term squared, 16a squared. The product of the 2 terms, 4 times 5 is 20ab. And then the last term squared, 25b squared. We have a match, a switch, and a plus. Same idea with our sum of cubes here. So the first term's cube root is 5c. The second term's cube root is 3. We are going to match the terms, or match the sign. And now to build the trinomial, square the first term, multiply the 2, square the last term, match, switch, plus. Factoring by substitution allows us to factor this polynomial as we would any other trinomial without having to expand the whole thing out, simplify it, and then try and factor it. We can substitute this matching binomial with another variable. So we're going to let p plus 3 equal x, and we'll just replace the expression. We'll have 8x squared plus 22x plus 15. Look for a GCF. We don't have one. Excuse me. So we'll go into our product and sum. So our product of 8 times 15, that gives us 120, and we want a sum of 22. So that's going to be, let's see, what do I want? 22, 10 and 12. Perfect. 8x squared plus 12x plus 10x plus 15. And now we can go into grouping. 4x, 2x plus 3, and plus 5. 2x plus 3. So we get 4x plus 5 and 2x plus 3. Now, the reason we pick a different variable than the one we have is to remind ourselves that, hey, I'm not done. This isn't going to be any of my factors because it's a completely different variable. So that is a reminder that we now need to take p plus 3 and substitute it back in for x and then simplify those resulting factors. So we're going to have 4 times p plus 3 plus 5 and 2 times p plus 3 plus 3. And we will expand both of those and simplify. So we distribute the 4, p plus 12 plus 5, which will then just be 4p plus 17. And distribute the 2, p plus 6 plus 3, which leaves us with 2p plus 9. And that is our final factorization. Now, all of those were expressions. There was no equal sign. If we have an equal sign, then we are able to solve. So we're going to solve the equation by using the zero factor property. That means we can factor the polynomial. So we will start by factoring it if it's not already factored. So leading coefficient of 1, so product of 16 and a sum of 6. That's going to be, negative 16. So we're going to use 8 and 2, and we need the 2 to be negative so that we get a sum of 6, and still get our product of negative 16. So we'll have x plus 8 and x minus 2 equals 0. Our zero factor property states that if we have a bunch of factors set equal to 0, like we have here, then one of those factors has to be 0 in order for that equation to be true. So we set both factors equal to 0 and then solve them independently. X equals negative 8 and x equals 2. The thing that will trip most people up at this point, because it's pretty straightforward, is having the wrong sign. That's going to be the number one mistake that probably happens. once you get it successfully factored is just forgetting to switch the sign. If I've seen it once, I've seen it 1,000 times. Okay, so just be very careful with your signs here. In order to apply our zero factor property and factor it, we have to have it in standard form first, which means we set our equation equal to 0. So we're going to bring both these terms to the other side by adding them. And so we have our trinomial with a GCF, so we can start by factoring that out and make factoring it much easier. And we want our product of 32 and a sum of 12. 32, a sum of 12, that's going to be 8 and 4. X plus 8 and x plus 4. And we can set each factor equal to 0. If I set 2 equals 0, there's no variable and 2 doesn't equal 0, so we can just ignore that factor. X plus 8 equals 0, and x plus 4 equals 0. Subtract 8 and subtract 4. So we're left with x equals -8 and -4 for our solutions. All right. And then this was still some more of Unit 1. Used to be Chapter 12. I extended Unit 1. Huh? Oh, did I miss one?
1 to 10.
Oh, up here. Thank you. We'll finish with Unit 1 after that. I guess we'll do this one. All right. No GCF, so we're going to do a product of 20 times 15. 300, yeah. 300 and a sum of 37. Anyone done that yet? No? Okay. All right, let's take a look here. 300. I want 37. That's going to be 12 and 25. So we'll split 37. We'll do plus 25x plus 12x plus 15 and proceed with grouping. So 5x and then 4x plus 5 plus 3, 4x plus 5. 4x plus 5 is one factor. 5x plus 3 is the other factor. Set both to 0. And my computer is running very slow today. Now we can solve. 4x equals -5, x equals -5/4. 5x equals -3, x equals -3/5. So we've got 5/4 and 3/5. So solving with factoring, we also have other methods of solving quadratic equations. Square root property only works when we have just a single x term inside of our polynomial. So x only appears one time in the entire polynomial, and it's either part of an expression that's being squared or it by itself is being squared. And so we can use our square root property, which just says, take the square root of both sides, and then we are left with the positive and the negative root of whatever that number is. If it's not a perfect square, we just need to simplify the radical. Since 8 can be broken apart into 4 and 2, we end up getting, we can take the square root of 4, which is 2, and we're left with a 2 still inside the radical. So x is positive -2 square root of 2. For this expression here, we can square root it before we can get rid of the 2 on the inside. 17 is prime and not a perfect square. So we're left with x minus 2 equals plus and minus the square root of 17. There's no simplification there, so we're just going to add 2 to both sides of the equation. So x equals, we typically put that number in front of the radical, so we have the plus minus between the radical and the rational number. So we've got 2 plus or minus the square root of 17. Again, your test next week is multiple choice, and depending on which textbook I pulled the question from, you could see it as the plus minus, or they will write it out separately as 2 different values within the solution set. So you may see 2 plus square root of 17 and 2 minus square root of 17. Just make sure the plus and minus is on the root and not on the 2. We can square root again. 4x minus 9 equals plus or minus root 7. No simplification there on the root 7. It is prime. And then we're going to add 9 to both sides to start. So 4x equals 9 plus or minus the square root of 7. And then we will divide both sides by 4. So a couple different ways you could see the answer depending on whether or not we can simplify. Here, this is one option since I can't simplify with 9 and 4, nor is there a coefficient in front of the root that we can simplify with. This is one way that you'll see the expression. Or again, you may see it written separately as 9 plus root 7 over 4 and 9 minus root 7 over 4. If some simplification could take place, you could alternatively also see it as 9 over 4 plus or minus root 7 over 4. See it written as 2 different fractions. These are all equivalent representations of the same number, just whether we have it as 1 fraction or 2 separate fractions. When we go to take the square root and we have a negative value, just remember that's a non-real number. So we have x plus 4 equals plus or minus the square root of negative 2. And we can split that as negative 1 and 2. And the square root of negative 1 is the imaginary unit. Where that I gets placed will also vary based off of basically whichever author is writing that textbook. So when you're looking at your answers or you're writing your answers, you want to consider, again, some equivalent representations. That I could be in the front. But more technically, if we're writing it in the form a plus bi, that I would be in the back. Just be very, very careful that it's not inside the radical symbol. It is separated from the radical symbol. It is clearly after the radical symbol. So just be very careful. And again, also it could be written as 2 separate values, negative 4 plus root 2i and negative 4 minus root 2i. So I can't force you to complete the square to solve a quadratic equation, but I can still force you to remember how to do the process. So being able to explain to me and demonstrate how to complete the square to make a perfect square trinomial and then be able to factor the trinomial. So again, I want this last term to be a perfect square so that it fits in the formula where we have a squared plus or minus 2ab plus b squared. So we're adding a term. The formula that allows us to complete the square is b divided by 2 squared. So we're going to take our b value, in this case 18, divide it by 2 to get 9, and then square it to get an 81. So 81 is the constant that we are putting there in order to complete the square. And then to factorize it, we just have x, and then we're going to take this number plus 9 quantity squared. We have that perfect square trinomial. Even if our b value is not divisible by 2 evenly, we can still apply the same process. So 1 divided by 3 divided by 2, and then that entire thing will be squared at the end. really bad looking too. So 1 divided by 3 divided by 2 is 1/6. And then we square 1/6 to get 1/36 as our constant. And then to factorize it, again, x, we're going to take that plus sign, and then the value we had before we squared it is what our constant is. So I have x plus 1/6 squared as the factored form. Okay. Typically, if we're asking you to use a quadratic formula, it's probably because the polynomial is not factorable. It's not guaranteed, but being able to have the quadratic formula in your back pocket to solve, especially if it's a non-factorable, because our solutions are either irrational or non-real. Just make sure that your equation is in standard form to start. So it has to be in the form ax squared plus bx plus c. If it's not, you need to rearrange the equation so that you're getting the proper values of a, b, and c. A being 1, b is -6, and c is 45. And we can plug it into our quadratic formula. X equals -b plus or minus the square root of b squared minus 4ac, all of that over 2a. I don't know why, but I've been seeing more and more of late students only putting the fraction on this part, and that, excuse me, that is not accurate. The fraction bar goes across the entire thing. 2a is the denominator of the entire expression. Excuse me, I've got the hiccups. So x equals -6 plus or minus the square root of -6 squared. When you square b, make sure you get a positive, because if you type into your calculator -6 squared, that's going to give you -36. What we want is -6 squared, which is a positive 36. So be very, very careful when you are squaring whatever your b value is, that you end up with a positive result. So make sure you're very diligent about keeping track of that. Times 4 times 1 times 45. All of that over 2 times 1. Again, I recommend doing this step by step because you can put the whole thing into your calculator, but you're probably going to mess up. And if your answer is irrational, it's not going to help you because you're looking for an exact answer with a simplified radical. So you want to take it piecemeal anyway. -4 times 45, 180 over 2. 36 minus 180. That's going to give us -144. So we know our solution is going to be non-real, and 144 is a perfect square. So we are left with plus or minus 12i in the numerator. And we can simplify this all by 2, leaving us with 3 plus or minus 6i, and no more having a denominator. And that's all we have time for this period. So we'll pause here and I'll come back in a little bit. I'll keep working on this for the next 30 minutes or so. And then I'll pick back up around 10:15 today. Any questions before we break? Okay, cool. I'm going to take a short break and then come back to this in a little bit. So let me image that. Oh, no, that's the wrong time. I'm going to be back before that. I need a new banner image. Oh, well. All right, I'll make a new one. Just need one that says be right back. Be right back.
Stay tuned.
Stay tuned. Smash that like button.
Subscribe. Put your favorite equation in the comment section.
There you go. Put requests for equations in the comments.
Ask me questions.
Alrighty, let's pick back up where we left off. Make sure this is still good. Yep. And do I have sound? Yep. Got sound. Okay, we are good to roll. All right. So made it pretty far down. We are now in the latter half of Unit 1 from the second quarter. We made it all the way through the SAT algebra. Did factoring, solving by factoring, square root property, all Unit 1 skills. Now we are solidly in the domain of quadratic formula. So 117 left us with imaginary solutions, 3 plus 6i and 3 minus 6i. And now we're going to continue. Again, just reiterating that with quadratic formula, make sure that we are in the standard form, ax squared plus bx plus c, so that we get the proper values for a, b, and c. The equation set equal to 0. In this case, a is 7, b is 8, and c is 2. And we can go ahead and plug into our quadratic formula. So we're going to have b squared minus 4ac all over 2a. Do you have your own calculator? Not a graphic calculator.
Oh, so I'm sure they'll also. Because like if you're
Yeah, you can do it outside. It's fine. As long as you leave your phone and smartwatch. All right, so we'll go through and simplify. So -8, 64, and then 4 times 7 times 2 gives us 56 over 14. We'll add 56 and 64 to get the square root of 120, which is not a perfect square, so we want to factor it and simplify. Perfect square factors of 120. Let's see. I know 4 will work. I'm going to see if I can go bigger. I think 4 might be the largest. Let's look at a factor tree. So 120, 4, and 30. And yeah, 30 doesn't have any perfect square factors, so we'll leave it at 4 and 30. So square root of 4 gives us 2, and then the square root of 30 stays in. And because we have a common factor with the 8, the 2, and the 14, all of them can be divided by 2. We can simplify. Again, this only works if all 3 of those factors have all 3 of those terms have a common factor. Notice we're doing nothing else with the square root of 30. It stays inside the radical. Again, I mentioned this earlier, just want to reiterate, sometimes you'll see this written as 2 different answers, just with the negative and the positive in between the rational number and the root. So just keep in mind, it may or may not have the shorthand, so just be on the lookout for that. Since we're talking about the quadratic formula, it's a good time to reiterate the discriminant. Remember that the discriminant is the value of b squared minus 4ac, which is the part inside the quadratic formula, inside the radical of the quadratic formula. It's just the b squared minus 4ac. That tells us the number and type of solutions we'll have because that's the value being square rooted. That is making the determining factor on whether it's rational or irrational, real or non-real, one or two solutions based on that value. So just a quick recap. If it is positive and it is a perfect square, then we are going to have two rational and real solutions. If it is positive but not a perfect square, we're still going to have two real solutions. They're just going to be irrational instead. If it is 0, we're only going to have one real solution because when we square root 0, if I added or subtracted, I'm just adding or subtracting 0, so it doesn't make a difference. And then if it's negative, doesn't matter whether it's a perfect square or not, we're going to get two non-real complex solutions. So we're looking at the value of the discriminant to determine which of these types of solutions we'll have and how many we will have. So again, we want to make sure we're in standard form. The value of A is 1, B is 5, and C is 4. So we have 5 squared minus 4 times 1 times 4. 25 minus 16 gives me 9. So it's positive, therefore I know my solutions are going to be real. And if they're real, we just need to look, is it going to be rational or irrational? Thank you. So two real solutions. Since 9 is a perfect square, I can take the square root of it. That means I'm going to have two real rational solutions. Two rational solutions. We are not in standard form, so we need to get it set equal to 0. Because my squared term is negative, I'm going to go ahead and move everything to the right-hand side. So I'm going to add 6a squared and subtract 9. So add 6a squared and subtract 9. And that's going to give me 6a squared plus 3a minus 4. So the value of A is 6, B is 3, and C is negative 4. So we're going to have B squared minus 4AC. There we go, minus 4AC. So 9 plus 96. And that's going to give me 105. 105 is not a perfect square, but it is positive, so we're going to have two irrational solutions. Two irrational solutions. So we're asked to solve, we're given a word problem, taking a look at the equation that's modeled. We are trying to find the time it takes for the ball to hit the ground. Since we're solving for time, that's our variable t. They have to then tell us what the height is when the ball hits the ground. At the ground, the height equals 0. So we set the equation equal to 0. Oops, it's 7D. Okay. And we'll use our quadratic formula. Since we've got the decimal in there, it's going to be really hard to try and factor it. So we can just go straight into quadratic formula. No point in trying to factor it. A is negative 4.9. B is 21. C is 70. So x equals negative 21 plus or minus the square root 21 squared minus 4 times negative 4.9 times 70 all over 2 times negative 4.9. In the past, with this type of problem, the biggest issue I see is the sign at the end. Getting the right numbers, but the signs are switched. Be very, very careful, because my numerator is negative and my denominator is also negative. That's that double negative property. Those are going to end up canceling out. Also be very careful with your multiplication on your intermediate steps. So we can take a look at negative 21 plus or minus 21 squared is 441. And then negative 4 times 4.9, make sure I get 4.9, not 49. And 70 means I'm going to have plus 1,372 over 4.9 times 2 is going to give me negative 9.8. We'll add inside the radical. If I can push the right buttons on my calculator, that would be good. So negative 21 plus or minus the square root of 1813 over negative 9.8. Now, hold on. I feel like I have an issue here. I don't want that. Are we still good? Yeah, I think we're still good. Sorry, just checking my stream. Hold, please. Trying to make sure everything's still running. All right, I think we're still good. Yeah, we're still good. Okay, I got it. Now, chances are, without actually doing any calculations, I know I'm going to have an irrational solution. 1813 is not a perfect square, because it says, hey, round your answer to the nearest tenth of a second. All right. So there's no point in trying to simplify that radical. At this point, we're just going to go into our calculations. So we've got two different calculations we need to run. We have negative 21 plus the square root of 181.13 over negative 9.8, or negative 21 minus the square root of 1813 over negative 9.8. Now, chances are we want to consider our answers by looking at the signs to see, would it be reasonable, which answer is probably going to work the best. We have this double negative, so this is going to cancel, but it's not going to affect that. But be very, very careful when you're doing your calculations. Oops, it's 9.8 to make sure we get the correct answers. So first we've got negative 21 plus the square root of 1813. Make sure that you add these in your calculator first before you do the division. Otherwise, it's going to divide first and then do the addition, which is going to give you a completely different answer. Okay, so the negative 21 plus the square root of 1813 gives us a positive 21.579 And then when we divide that by negative 9.8, it's going to give us a negative number. It's going to give us negative 2.2, and that's just not going to work. So we want to go back to the subtraction version, the negative 21 minus the square root of 1813, and divide that by negative 9.8, and that's going to give us a positive 6.487, blah, 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 blah. That is going to be our only reasonable answer because time can't be negative. Round to the nearest tenth, which is that 4 there. The 8 will tell that 4 to round up, so we're going to have 6.5 as our value for time. So now we're given another equation modeling height and time. We want to find the time. So again, we're solving for t, that the ball will be 30 meters from the ground. So they're telling us the height equals 30. So we'll replace height with 30. And then we'll set it equal to 0 by subtracting 30 from both sides. And then we repeat with our quadratic formula. Going to square 42 first. 1,764. Then negative 4 times 4.9 times 70 gives us 1,372 over negative 9.8. And then we're going to go ahead and add the discriminant together. Negative 42 plus or minus the square root of 3136 over negative 9.8. And again, we're going to solve both of these. One with the plus, one with the minus. So starting with negative 42 plus the square root of 3136, we evaluate that, we get 14. And then when we divide that by negative 9.8, we're going to get some negative number, which is not going to be a valid solution. We get negative 1.4, which just doesn't work. So we go back and do the subtraction version and divide that by 9.8. And, oh, I messed up. Hold on. Oh, it would help if I put in the negative. I'd get positive 10. That's why I messed up. Try that again. There. Divided by negative 9.8. Yeah. All right. So we end up getting a positive 10. And that is our valid answer. All right. Now we're moving into the second unit of our second quarter with our synthetic division, remainder theorem, rational zeros theorem, factor theorem. So this was the last couple weeks of our quarter. So again, the key here is a lot of these questions start out the same with synthetic division. Big things to pay attention to. One are the signs. Make sure that you're using the correct signs on all of your numbers. And then what is the question asking for? What am I doing with the result of the synthetic division? Am I writing a quotient? Do I just need the remainder? Is it yes or no? Why is the answer yes or why is it no based on the result that we're looking for? Do I need to factor? Do I need to solve? How much work goes into continuing that? after I get my first round of synthetic division. What do I need to do after that? If we're just trying to perform the division, we just want the quotient. So we're going to set up our synthetic division with our 0 of -2. So we're going to put -2, and then making sure that you've got all of your values accounted for. So 3, 2, I'm missing my linear term, so I need a placeholder 0, 1, -1, 0, and 4. And then we just perform the division, and we're going to write our quotient from that. 1, -2, -3, 6, 6, -12, -8. Our quotient will always be 1 degree less than what we started with. So we're going to have x squared minus 3x plus 6 plus -8 over x plus 2. We write the remainder over the divisor to get our full quotient and remainder. Here we're going to use +6 for the synthetic. We've got 4, 3, 2, 1, 0. All numbers are accounted for. So we can go ahead and set up that top row. 1, 6, 2, 12, 3, 18, 1, 6, 0. Since we got a remainder of 0, we have no remainder, so we're just going to write our quotient 1 degree less. This will be x to the third. So x to the third plus 2x squared plus 3x plus 1, and there's no remainder, so we don't need to write anything else after the constant. Using synthetic division and the remainder theorem, we're going to evaluate f of k. That means we're going to get a number that equals, we're solving for f of -2, or we're solving for f of -3 using the remainder. Students always ask, why can't I just plug in -2? Well, go for it. Go ahead and plug in -2 to each of those y values, calculate each of those, and don't screw it up in the process. Good luck. That's going to take you a solid probably 3 to 4 minutes to get that and make sure that it's right. That's why the remainder theorem is so powerful. It allows us to evaluate these higher degree polynomials for these specific values of x with much less room for error. So again, it's really important to remember that usefulness of synthetic division. So we don't need to switch the sign because we're given the 0, we're given the value of x. We got to just make sure that we have all of our degrees accounted for. 6, 5, 4, 3, 2, 1, 0. We're good. So we can set up all of our coefficients. It would help if my pen would continue to write. There we go. -4, 3. Oh, come on. I think the battery's dying. Okay, there we go. -4, 1, -2, -4, 3, 2, 5, and 5. All right. So again, we're just trying to find the value of the remainder. So 1, -2, -4, 8, 4, -8, -5, 10, 12, -24, -19, and 38, 43. All right. I am going pretty fast at those, so if I mess up a sign or something, please call me out on it. I'm not too proud to admit when I make a mistake. So we're just looking for the remainder, which is 43. That means that f of -2 equals 43. Was the value of that function at that x value. All right, same thing again. We've got 6, 5, 4, 3, 2, 1, 0. So we're accounted for there. 1, -2, -2, -3, -3, 5, and 7. 1, -3, -5, 15, 13, negative 39, negative 42, 126. Yeah. 126, 123. Now these numbers are getting too big even for me. Negative 378. And, oh, no, sorry, I multiplied the wrong number. Go back, not that. 123 times negative 3. Yeah. 369, negative 369. And negative, my pen stopped working again. Hold for technical difficulties, please. There we go. Negative 364, 1,092, 1,099. So f of negative 3 equals 1,099. Continuing with the synthetic division, we want to decide whether it's a 0 or not. It's a 0 if the remainder is 0. So again, it's a yes or no question based off of the remainder of the polynomial. So we'll do our synthetic division. We're missing our third degree and our first degree, so we need placeholders for the 3 and the 1. So 4, 3, 2, 1, 0. All of our numbers are accounted for. 1, 2, 2, 4, 11, 22, 22, 44, 0. Since our remainder is 0, yes, 2 is a 0. So we'll set the same thing up again. We've got 4. We're missing the 3. 2, 1, 0. So we just need a placeholder for the 3. Negative 1, 2, 2, negative 4, negative 7, 14, 13, negative 26, negative 29. No. Negative 2 is not a 0 because we have a remainder. Same idea with the zeros. Checking to see if a number is a 0. The same principle applies for determining if it's a factor. The only difference is we're given the factor. So we test the 0. If the 0 is a 0, then the factor is a factor. So we're looking for that remainder of 0. So the 0 that corresponds with x minus 1 is just a positive 1. 1, negative 3, 7, negative 5. 1, 1, negative 2, negative 2, 5, 5, 0. So yes, x minus 1 is a factor because 1 is a 0. The 0 that corresponds with x plus 3 is negative 3. So we want to see if negative 3 is a 0. 9, so 4, 3, 2, 1, 0. We've got all our numbers. 9, 26, negative 3, 1, and 4. 9, negative 27, negative 1, 3, 0, 0, 1, negative 3, 1. Since our remainder is not 0, negative 3 is not a 0, therefore x plus 3 is not a 0. We are almost done. Is this the last page? 2 more pages. 3 more pages. Oh, it's a bunch of graphs. That's why. That's right. So we're given a 0. We want to factor it into linear factors. Every time we do the synthetic division, we get a remainder of 0. We have then successfully factored the polynomial, and we just need to get to a quadratic, so then we can factor it normally from there. So we'll use 6. If my pen works. Man, I'm having trouble with my pen today. And I just changed out the battery too, the shenanigans. See if that fixed it. There we go. All right, 1, -3, -36, 108. We're told this is a 0, so it has to work. If it doesn't work, then we messed up. So what do we have there? 3 and 18. And then we get -18. And just to double check, even though I'm pretty confident, yep, -108. And there's our remainder of 0. So our quotient that we're left with is x squared plus 3x minus 18. We're looking for linear factors, so we know this will be factorable. With our product of -18 and the sum of 3, we're going to use the numbers 6 and -3. So x plus 6 and x minus 3. Now this is a 3rd degree polynomial, which means we have to have 3 factors. We only have 2 right now. The 3rd one comes from the 0 that was given. If x equals 6, then the factor that gives us that is x minus 6. So our final factor is x minus 6. Here we're given this lovely imaginary number, and we're told that it's a 0. So we have to end up with a remainder of 0. If you make sure that your calculator is in non-real mode, as long as you put your complex numbers in parentheses, it'll do the adding and subtracting and the multiplying for you, which will save you a lot of space. Otherwise, you have to use distributive property. So 2i is our 0. We have 1. We've got -4 minus 2i. I just distributed that negative into there. And then we've got -5 plus 8i. And then we have 10i at the end. So 3, 2, 1, 0. Bring down the 1. We multiply it by 2i. We add these together. The 2 i's are going to cancel, leaving us with -4. Multiply by 2i, we get -8i. Those are going to cancel, leaving us with -5. Multiply -5 by 2i, we get -10i. That gives us our remainder of 0. So that all worked out. We're left with x squared minus 4x minus 5, which again is factorable, x minus 5 and x plus 1. And then again, 3rd degree, which means we have to have a 3rd 0 or 3rd factor. If x equals 2i, we can set that equation equal to 0, and we get x minus 2i as the last linear factor. Here we're given another 0, but we're given it with a multiplicity of 2, which means that -2 is a 0 twice, which is good because we have a 4th degree polynomial. It'll take 2 rounds of synthetic division to get a quadratic. So we'll start with -2, 1, 4, 1, -12, -12. 4, 3, 2, 1, 0. 1, -2, 2, -4, -3, 6, -6, 12, 0. So right now, what we have is x cubed plus 2x squared minus 3x minus 6, okay? Doesn't do me a whole lot of good, so we're going to do synthetic division again with that new polynomial to get all the way down to the quadratic. So -2 again, because it had a multiplicity of 2. 1, 2, -3, -6. And that leaves us with x squared minus 3. Now, our first two factors will come from the -2. So we have x, if x equals -2, x plus 2 equals 0. So we'll have x plus 2 squared. So now there's a couple different ways that we can approach this. We want to look at the directions, and it says factor into linear factors. So we have this quadratic here, and it's not typically factorable, not with integer coefficients, but it's also not linear. So we can still factor it kind of using the zeros to our advantage. These factors just aren't going to be very pretty. So we take x squared minus 3 and we set it equal to 0. And we solve, and we get that x equals positive and negative square root of 3. Just like what we did up here, we can use those zeros to basically factor this quadratic to that final step. So if x equals square root of 3, we subtract it from both sides. X minus the square root of 3 is one of my factors. And if x equals negative root 3, we can add it to both sides. This pen is driving me insane today. I haven't had any issues so far. I blame you guys. You broke it. It's all your fault. We get x plus the square root of 3 as our other factor. So our linear factorization, x minus root 3, x plus root 3, and x plus 2 squared. And that is our complete factorization. So here for the polynomial, 1, 0 is given. We want to find all the others. So again, we've given something to start with, and we're just going to kind of take it from there. So we're given a 0. We want to find the rest of them. Checking to make sure we have all our degrees, 3, 2, 1, 0. We get our remainder of 0. We have x squared minus 2x plus 5. Do a quick check to see if you can factor it. We can't because there's no product of 5 that adds to -2. So the only other way to find the zeros is use quadratic formula. A is 1, B is -2, and C is 5. So we're going to have negative B plus or minus the square root of B squared minus 4AC over 2A. 2 plus or minus 4 minus 20 over 2. 2 plus or minus the square root of -16. Now we see why we couldn't factor it. We're going to have non-real solutions. The square root of -16 is 4i. And then we can simplify both of these. All those divide by 2, leaving us with 1 plus and minus 2i. It said find all other zeros, so we don't need to list the one that was given. We just have to give the zeros that we found after that synthetic division step. Here we're given a 0 of I. Thought I took this question out, but I must have missed it. But we'll do it anyway because it's a fun one. I like it. It's actually really easy. It looks like it's not, but it is. 4, 3, 2, 1, 0. We've got all our degrees. So we've got 1 times I is 1I. When we add negative 10 to that, we have negative 10 plus 1I, or just I. And then we're going to multiply. So again, remember, when you're multiplying your complex numbers, you have distributive property. We're going to end up with negative 10I plus I squared, and I squared equals negative 1. So we have negative 1 minus 10I. Negative 1 minus 10I. Add these together. We add the real terms, so we get 22 minus 10I, which again, 22 minus 10I being multiplied by the I, that distributive property. So 22I minus 10I squared, since I squared is negative 1, that turns that into a plus 10. So 10 plus 22I, 10, oopsies, let's get rid of that. 10 plus 22I. Those 10s will cancel, leaving me with 22I. Multiply that by I, that gives me negative 22, and then I get my remainder of 0. And so now I'm left with this not very pretty quotient. I started with a 4th degree, so I know that this is now a 3rd degree. We're going to continue doing synthetic division, and there's an implied 0 that's given with this one. Imaginary zeros always come in pairs where you switch the sign. So if I is a 0, negative I is also a 0. So we can do the synthetic division again with a negative I, and then using this bottom line here as our numbers. And as we do that, it's going to cancel out all of those imaginary parts. Not letting me scroll. So 1, negative I, those are going to cancel, negative 10. Multiply, 10I, those are going to cancel, 22. 22, negative 22I, those are going to cancel, giving me 0. So now I'm left with x squared minus 10x plus 22. From there, we can either try and factor or quadratic formula to find the other 2 zeros. I'm going to take a break from here, and then I'll pick back up at about 12:45. You guys are the first one, aren't you? Are you the first exam next week?
Yes.
Monday at 7. Monday at 7:45. Bright and early. Please make sure you come with a pencil. You need a pencil for your scan sheet. And make sure your calculator is charged, please.
Are we in this room? Yeah, right?
Yeah, you're in here. Pencil and calculator is all you need to bring. You can leave everything else.
Are we gonna need the scientific calculator?
Graphing calculator is fine.
Are we gonna get what we had this past weekend?
We'll use some of that. You're not gonna have to graph one by hand, but you'll have to be able to analyze a graph. Take care. Oh, no, I muted myself. Let's try that again. Now I think I'm good. Yeah, I should be good. There we go. Okay, should be good now. I'm glad I checked that. All right. So when you have I as one of your zeros, negative I is also zero. It's called its complex conjugate. They always come in pairs. You can never have just one imaginary number zero if all of your coefficients are real numbers. So I was able to do synthetic division not only with the I and end up with that cubic polynomial, but I can also do the synthetic division again with negative I, and that gets rid of all the complex coefficients, and I'm left with a quadratic. And then from there, we can either try and factor the quadratic or solve. This one's not factorable, so we're going to use quadratic formula to find the other zeros, where A is 1, B is negative 10, and C is 22. Get my calculator back. As much as I want to do the math with 22 in my head, I don't. So X is negative 10 plus or minus the square root. Negative 10 squared minus 4 times 1 times 22 over 2 times 1. So going through and simplifying the quadratic formula there, we get 100 minus 88 over 2. So we have 10 plus or minus the square root of 12 over 2. We need to simplify the radical before we try and simplify the fraction. We cannot reduce that 12 with the 2 in the denominator. So we can split 12 into 4 and 3. So that gives us 10 plus or minus 2 root 3 over 2. And that lets us simplify these as 5 plus or minus root 3. So the rest of our zeros are 5 plus and minus root 3, as well as the negative I that we used in the second set of synthetic division.
Sorry, why negative I?
Imaginary zeros always come in pairs. So if we had I as 1, we also have to have negative I. Here we're going to give the possible rational zeros for the following polynomial. So we're not going to find the actual zeros. We're just creating that list. So that's our P's over Q's. P is the factors of the constant over the factors of the leading coefficient. So factors of 27 include positive negative 1, 3, 9, and 27. Factors of 3 include positive negative 1 and 3. Yep.
Question.
Yep.
Why in the other one is only negative I and not positive I and negative
I was given, and if I is a 0, negative I also has to be a 0.
So the both of them are zeros.
Yes. Okay. I was given, negative I has to be a 0 as well. So we're going to create a list of fractions from this ratio. We're going to take every numerator and pair it up with every denominator. So 1 over 1 and 1 over 3. So that gives us positive negative 1 as well as positive negative 1/3. 3 will get matched up as well. Positive negative 3. 3 over 3 is 1, which we already have. We'll repeat with 9. Positive negative 9. And with positive negative 27. So this gives us a list of possible rational zeros. If our polynomial has rational zeros, they will be on this list. That leads into polynomials that we need to completely factor and find the rational zeros, and we're not given any. We have to use that list to determine what numbers will work and which ones won't. So we'll start with P's over Q, and we'll look at our factors of negative 90 over our factors of 1. So positive negative 90 over positive negative 1. Since our denominator is 1, it's just going to be integers. We're not going to have any fractions, so we can just look at all of the factors of 90, which include positive negative 1, 2, positive negative 3, positive negative 4, 6, 6, positive negative 9, 15, 30, 45, 90. Let's see if I got them all. 45, 3 and 30,
Wait.
4 and 15. Oh, and 10. I missed 10.
This 4 one.
No, I was thinking 64 is not one. But I did miss 10. Come on. Going slow today. I did miss 10. Okay, so that 6, 6, and 15. Okay, there we go. So our rational zeros are somewhere on that list. That's a lot of zeros to check. So this is where we use our graphing calculator to check to see what our actual zeros might be. We just need to find one that works for our synthetic division. So I'm going to graph this off the screen, but I can sketch it here just so we can see. Our graph gives us our passes through -6, comes back down, passes through 3. It's a really beautiful graph. Passes through 3, and then comes back up and passes through 5. 1, 2, 3, 4, 5. Okay, so we have these possible rational zeros that we can use for synthetic division. Oh, I forgot 5. 5 and 1. 5 and what's that? 18. Forgot 18 as well. Okay. So we've got our best guesses as either -6, -3, or 5. We can use any of these numbers for synthetic division to try and factor the polynomial. We should have a remainder of 0. Let's use 5 just because it's positive, so we won't have to worry so much about sign switches. Will probably be a whole lot easier. So we get 1, 5, 9, 45, and 18, and 90, and 0. So we get that remainder of 0, so we know that 5 was a 0, so we successfully factored that for the first step. We're left with x squared plus 9x plus 18. So we can continue to factor that. Product of 18 and the sum of 9, we're going to use 6 and 3. So x plus 6 and x plus 3. There's 2 of my factors. I need a third one. So we're going to pull from the first 0. Guess we don't want to change pen color. If x equals 5, then that means that x minus 5 is one of our factors. So our third factor is x minus 5. And then all of our zeros are x equals 5, x equals -6, and x equals 3. So we've got our factors and our zeros for that polynomial. Please scroll. Pause for technical difficulties. There we go. Okay. Repeat the process again. We want to check what our list would be. Factors of 28 over factors of 1. 1, 2, 4, 7, 14, and 28. And then we can go ahead and graph it. X to the third minus 7x squared minus 4x plus 28. So when we look at our graph, it looks like we have an intercept at -2, at +2, and over here at 7. Our graph comes up, comes down, comes up again, 2, -2, 2, and 7, all of which are numbers on our list. So we can make our best guesses, and let's just pick 2 for synthetic division. 2 doesn't work, we can switch to another number. We just need to make sure we get that remainder of 0. And we do, leaving us with x squared minus 5x minus 14. We can factor. Product of negative 14 and a sum of negative 5 is going to be negative 7 and a positive 2. So x minus 7 and x plus 2. Again, our first factor will come from the first 0 of 2. So x minus 2. And then all of our zeros are based on solving each of these polynomials where x equals 2, x equals 7, and x equals negative 2, validated with the graph that we can sketch out as well. You good? Okay. Here we've got some that are already factored, so we just want to find the zeros and state their multiplicities. So again, remember, multiplicity is how many times a 0 shows up. So since it's already completely factored, we can set each factor equal to 0 and solve. So x will be 0, x will be 4, and x will be negative 12. None of these are squared or third or raised to any exponent, so all 3 of them have a multiplicity of 1. Here we can set our factors equal to 0. 5 doesn't equal 0, so we can ignore it. We have x plus 9 equals 0 and x minus 9 equals 0. So we get x equals negative 9 and x equals positive 9. When x equals negative 9, because our factor was squared, we have a multiplicity of 2. And because x minus 9 was cubed, when x equals 9, we have a multiplicity of 3. Okay. Remember, this affects the shape of the graph at those points. So our graph here at negative 9 is going to it's going to come up and it's going to touch the graph, and then it's going to come back down. While at positive 9, it's going to go up to the graph. It's going to bend, cross over, and then continue in the other direction. So this gives us a touch on the graph versus a bend on the graph. We'll use that to our advantage to identify some graphs later.
So this thing that it bends, crosses, and then goes up, is any multiplicity that is like odd more than once?
It's going to bend if it's odd and more than 1.
And one is
One's just going to go straight through. Yeah. I thought I took this question out. We're going to skip that because we didn't cover that this year. I covered it last year, but I didn't get to it this year. All right. So we want to find the equation given the graph. And so we're going to be looking at things like intercepts and behavior, as well as maximum number of zeros. So when we're looking at this graph here, we know it's going to be an odd degree polynomial because our end behavior goes in the opposite directions. And because the right side goes up, we know we're going to have a positive leading coefficient. So that's going to eliminate option D because it has the wrong leading coefficient. We see here we have a y-intercept at negative 5. So that's going to get rid of option 3. Because we only have 2 turning points and we have 3 x-intercepts, then that makes B our most likely option for this polynomial. We don't have enough bends in there for it to be a 5th degree, which would have 5 intercepts and up to 4 turning points. Here again, our opposite end behavior. So we know we're going to have an odd degree that eliminates option B, which is a 4th degree polynomial. We know that our leading coefficient is going to be negative because the right side goes down. So that eliminates option C. And then again, just like before, we can look at the intercepts. This one has a positive 12. That gets rid of option D. So A is the only one that works there. Both ends go in the same direction, so we're going to have an even degree polynomial that gets rid of A and B. Because the right side goes up, we know we're going to have a positive leading coefficient that gets rid of option D, leaving us only with C. Our graph ends go in the opposite direction, so that's our odd degree polynomial that gets rid of option D. We have the right side going up, so our leading coefficient will be positive. That gets rid of option C and A. And then we can verify that we also have the correct y-intercept with option B. So here, just like with the rational zeros theorem, we have a polynomial. We can factor it by using the graph. And what we can actually do is by knowing our multiplicities, we don't even need to go through the synthetic division. I can see that I'm passing through here one time at x equals -3. So that's a multiplicity of 1. So that's going to give me a factor of x plus 3. I'm touching the graph at 2 and then bouncing back up. That means I have a multiplicity of 2. So where x equals 2 gives me a factor of x minus 2, that factor is going to be squared. So the factored version is going to be x plus 3, x minus 2 squared. No need to do synthetic division because of the multiplicity.
Why don't we hate this?
Because it touches the graph and it turns back around. It doesn't cross over. Because even multiplicities don't pass through. They touch the graph and they turn back around. So here we have zeros at -3. We have a 0 at -1. We have a 0 at 1, and we have a 0 at 2. All of these are multiplicities of 1 because they pass straight through. And we can only have up to 4 zeros anyway because of the degree. So we can get our factor of x plus 3, x plus 1, x minus 1, and x minus 2. So here again, we have a 4th degree, so we should have 4 zeros. We've got 1 at -3. We've got 1 at 0. We've got 2 at 2 because, again, we have that bend. So we have another multiplicity of 2. So x plus 3. And then x equals 0 is just x. Whenever we pass through the origin, our factor is just x. And x minus 2 for this 0 with a multiplicity of 2. And that's it. We did it. Questions, comments, concerns, queries, conundrums? You're strange.
Can you curve the midterm for us?
No. Nice try, though.
Is it 100 questions?
75.
It's approximately 75. I don't remember exactly. It's somewhere between 70, 80, which is where I usually keep my midterms. Between 70 and 80.
all multiple choice.
It is all multiple choice.
Oh, thank you.
But here's the problem.
A, B, C, D or A, B, C, D, E?
It's ABCD,
Okay.
but y'all get super excited about multiple choice, but you forget math is not like the other subjects. All the answers look, you can't just guess if you don't know what to do.
Serious, think about it.
No,
It's
it's,
just 40
it's not that. It's just if we don't know the answer, we still have at least
25.
somewhat of a chance.
You have a
of getting
25% chance of getting it
Exactly.
right.
I'm not relying on that, but if we
Come
don't
on.
know an answer, I'll
But
take
you're
a
relying on that.
25
You always-
over 0.
That's fair.
You're always using the Snapchat AI. So
Alrighty.
Can you do
It's coming today.
the question that comes before the 68th one?
Instead of the end of class. Wait, what are those class?
Which one?
The 60.
The what one?
67.
Number 67? I already did that.
I know.
I'm not doing it again.
This PDF, you're gonna like.
That gotta be racist. Oh, now you wanna talk about that gotta be racist when you guys say
Yeah,
something
we
against
go
every day. But you want to
That's too much work. We're gonna have something like that.
You know,
Yep.
yeah, I know.
Come on.
They put it in the
Enjoy.
How much time is our
They
question?
Google with the coach.
You get 2 hours and
The
15
coach
minutes for your
keeps
exam.
So
You know
that's
what?
You could play safe.
3.
Definitely.
2.
Why?
2 to 3.
That's so fun. Like, I really could get him kicked out.
All right. Thanks for watching. Later, taters. Boom.
How many viewers do you actually have?
See.